class, 30 days challenge. You're all welcome. You're all welcome. Please, as soon as you come in, let me know if you can hear me and let me know if you can see the board clearly. As soon as you come in, let me know if you can hear me and let me know if you can see the board clearly. If you can hear me, let me know. Welcome to day 4. Welcome to day 4. Welcome to day 4 of the Jamb Master 30 Days Challenge Chemistry. Today we're looking at chemistry. You're all welcome. 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 Please get your writing materials down and let us get started. Get your writing materials down and let us get started. Get rid of all distractions around you. Get rid of all distractions around you. There's no time to waste. Get rid of all distractions around you and let us get started. You are all welcome. You are all welcome. You are all welcome. Get rid of all distractions around you. Let us get started. Get rid of all distractions around you. Let us get started. If you can hear me, say I can hear you, sir. If you can see the board, say we can see the board, sir. If you can hear me, say I can hear you, sir. If you can see the board clearly, say I can see the board, sir. If you can hear me, say I can hear you, sir. You can see the topics we're looking at today: atomic structure, quantum theory, and periodic table. Atomic structure, quantum theory, and periodic table. Atomic structure, quantum theory, and periodic table. You are all welcome. You are all welcome. You are all welcome. As soon as you come in, if you can see the board clearly, let me know. If you can hear me, let me know. Give me the go ahead and we'll start. Give me the go ahead and we'll start. Give me the go ahead and we'll start. You are all welcome to day 4. You are all welcome to day 4. You are all welcome to day 4. Welcome, 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 welcome. Day 4. We're looking at atomic structure, quantum theory, and periodic table. Atomic structure, quantum theory, and periodic table. Welcome to day 4 of the Jamb Master 30-Day Challenge. Welcome to day 4. Welcome to day 4. Today is chemistry day. Today is chemistry day. Today is chemistry day. Let me know if you can hear me. Yes, yes, Francis said active. Let me know if you can hear me. If you can see the board clearly, say, sir, I can see the board clearly. If you can see the board clearly, say, sir, I can see the board clearly. If you can hear me, say, sir, I can hear you. We can hear you, sir. Sir, we can hear you, sir. You can see the board clearly. Let us know, let us know, let us know. Welcome, welcome, welcome. Yes, so I'm going to the board to start now. Yes, Binta said I can see the board clearly. Kelvin said I can see the board clearly. Joy Maxwell said I can hear you. So Omawumi says I can hear you. That's good. That's the go ahead for me to start now. That is the go ahead for me to start. That is the go ahead for me to start. You are all welcome to the Jamb Master Day 4 Chemistry class. Yes, you are all welcome to the Jamb Master Day 4 Chemistry class. Welcome everybody once again. Today we are looking at atomic structure, quantum theory, and periodic table. If you missed day 1, day 2, and day 3, you have nothing to be bothered about because the class was fully recorded. And if you notice, I kept posting it on the group back to back. But in case you just joined and I've not posted it again, I will post it again. Day 1, day 2, and day 3 is well recorded. So no cause for alarm. Even this day 4, not everybody's around now. We have over 200 students on the group, but not everybody's live now, right? They all go and watch it, so don't worry yourself. That's the advantage of an online class. So nothing to be bothered about. It's all recorded. Also, before the day 1, day 2, and day 3, there are 2 videos you should watch. Before you start watching day 1, day 2, and day 3, there are 2 videos you should watch. I also sent them on the group. That was what I thought the foundations of chemistry. Those 2 videos you should watch contain some things that will help us to be faster today. For example, we're looking at atomic structure today. Normally, I should start introducing you to atomic number, atomic mass, but I've taught all those things before, right? I've taught it in those first 2 videos. Yes, so I will not be starting from there. It's just for you to go and watch it. I will send the link to the video to the group. Don't worry yourself. So that we can go straight to quantum number. I remember I've taught atomic structure. I've taught our students who discovered the neutron and in what year, who discovered the electron. Let me know in the comment section if you still remember. What scientist created for discovering the proton and what year? Who discovered the neutron and in what year? Let me know in the comment section. Let me know who is still following us. Who discovered the electron? In what year was the electron discovered? And who discovered it? Let me know in the comment section. I've taught it in our first 2 chemistry classes, even before we started the 30-day challenge. I've taught it and they are all recorded. So don't worry, if you are new here, you're just coming, don't worry yourself. Anything you have missed was recorded. It's just what to send for you and you watch again from the beginning. No cause for alarm. Are we together? So I've taught a lot of the atomic structure already. A lot of the atomic structure has been taught already because we have done it on day 1. On day 1, we have taught atomic number, we have taught atomic mass. So I want to go straight to quantum theory. Quantum theory straight away. I hope you can hear me from the board. You know, it's one thing to hear me when I was standing behind, and one thing to hear me when I'm on the board. If you can hear me from the board, let me know again in the comment section, just to be sure. If you can hear me on the board, let me know in the comment section. Let me know in the comment section. Let me know in the comment section if you can hear me clearly from the board. Let me know in the comment section if you can hear me clearly from the board. If you can hear me clearly from the board, let me know in the comment section. Class, the quantum theory was proposed by a scientist known as Max Planck. And he said energy is released in small packets. So atoms release energy in small packets called quanta. Atoms release energy in small packets called quanta. Atoms release energy in small packets called quanta. And he gave an energy equation. Max Planck gave an energy equation. And according to Max Planck, he said that energy released by an atom is equal to h, which is the h stands for the Planck's constant, and v, which is the frequency of release. H is the Planck's constant, and v is frequency of release. E equals to h times v. Energy released by an atom. We're looking at atomic structure and quantum theory. Atomic structure and quantum theory. Atomic structure and quantum theory. It said the energy released by an atom is equal to h, which is the Planck's constant, times the frequency. H is the Planck's constant, and v is the frequency. Well, but don't forget that in wave particle motion, we know that the velocity or speed, if we are to break down frequency, you're going to find out that the frequency v is equal to the speed of light all over the wavelengths. The frequency v equals to the speed of light c all over the wavelengths. Meaning that we can replace this v with c all over lambda. Lambda stands for wavelength. This symbol represents lambda, which is wavelength. Wavelength. This c represents velocity of light. This c represents velocity of light. This symbol is lambda, wavelength, and this is the frequency. So frequency is velocity of light divided by wavelength, lambda. So it means I can replace this frequency with what? With velocity of light all over what? Lambda. So the energy stored in an atom, packed in an atom particle, is hc all over lambda. Hc all over lambda. write down, so I'll go to Niels Bohr atomic theory. Niels Bohr atomic theory. Niels Bohr. Bohr's model of an atom. Bohr's model of an atom. Bohr's model of an atom. Let us go to Bohr's model of an atom. Bohr's model of an atom. Bohr's model of an atom. Don't forget, let's make our commitment now. Every day we make a commitment in our class. I will not live till the end. I will not live till the end. I want you to type in the comment section, I will not live till the end. Your exam is getting closer and closer. Type in the comment section, I will not live till the end. Let's make that commitment. I will not live till the end. Make that commitment right now. I will not live till the end. I will not live till the end. Make that commitment. Make that commitment. There's a power when you say something. There's a big power that when you say something. Type it in the comments. I will not live till the end. I will not live till the end. I will not live till the end. Let's look at Bohr's atomic model. Class, this was proposed by a scientist known as Niels Bohr. And he said that electrons move in fixed circular orbits. Electrons move in fixed circular orbits around the nucleus. These orbits are called energy levels or shells. These orbits are called energy levels or shells. These orbits are called energy levels or shells. Class, the electrons in an atom move in fixed circular orbits around the nucleus. Class, if you watch the first day we had ever had chemistry class, not day one, I'm talking about the first chemistry class, those two other videos before day one, those two other videos, I mentioned that an atom is made up of proton, neutron, and electron. So an atom is divided into three subparticles: proton, neutron, and electron. We said the protons are positively charged, the neutrons are neutral, and the electrons are negatively charged. Then we also said that the proton and the neutron are stored deep within the nucleus. They are stored where? Deep within the nucleus of the atom. These two guys are deep within the nucleus of the atom. But the electrons are not in the same place where the proton and neutron are. This is why the electrons are volatile. They can easily be lost or gained. This is why in chemistry you hear of loss of electron, gain of electron. You never hear of loss of proton or loss of neutron. Always loss of electron. Why? Electrons are not stored inside. They are stored outside the orbits of the nucleus. Look at, according to Niels Bohr, electrons move in fixed circular orbits around the nucleus. These orbits are called energy levels or shells. So the electron form shells around the nucleus of the atom. And these shells are referred to as what? The energy levels. The energy levels. Class, we're looking at quantum theory, so don't be surprised if we're talking about energy a lot. Because the word quanta actually means energy. Quanta is singular and plural. Quantum and quanta are singular and what? Plural. Anytime you hear the word quanta or quantum, it means energy. It means what? Energy. So in this aspect of chemistry, we want to look at the energy levels that exist in atoms of elements. The energy levels that exist in atoms of elements. And different scientists came forward with different propositions. We have just looked at Max Planck's theory. We are now seeing what Niels Bohr's atomic model is telling us. And this Niels Bohr's atomic model is an improved version of Planck's model. Because according to Bohr was one that actually explained and exposed that electrons are actually found on energy levels or shells. And class, There are actually 4 energy levels. We have level 1, level 2, level 3, and level 4, depending on the type of shell. For level 1, we have the K shell. For level 2, we have the L shell. Level 3, we have the M shell. Level 4, we have the N shell. 4 energy levels. Class, these energy levels are represented with N. So for level 1, it means that N equals to 1. For level 2, it means that N equals to 2. Level 3, N equals to 3. And level 4, N equals to 4. These are the energy levels of what? That are found in atoms. Class. So N can be 1, N can be 2, N can be 3, N can be 4. The first calculation that you need to find out is that you could be asked to calculate the maximum number of electrons that can be found in an atom. Maximum number of electrons, that can be found in a shell. And the formula is 2n raised to power 2. So class, if given the energy level or the shell number of an atom, you can actually predict the maximum number of electrons that can be stored. You can actually predict the maximum number of electrons that can be stored. Applying the formula here, you see that 2 raised to n, what is n? 1 raised to power 2. 1 raised to power 2 is 1, 2 times 1 is 2. This is why the K shell can only store 2 electrons. If you come down here and apply the same formula, 2n squared, that's 2 squared. This will give you 8. You come here, you say 2 times 3 squared. 3 squared is 9. 9 times 2. You have 18. That means an element that contains K element shell can only have 18 electron maximum. And an element that has K element, you have 2 into bracket 4 squared. And 4 squared, 16 times 2 is 32. 32. Now let's actually look at how the quantum numbers now come in. How do quantum numbers come in? Let's look at quantum numbers. Quantum numbers. Class, notes. I also might not be confused and say that about M shell can only take 8 electrons. Class, we're not talking about how many electrons that M shell can take now. We are talking about how many electrons an atom that contains KLM can take. How many electrons will an atom containing KLM? Because if you are in the third energy level, it means that you have passed through the first, second, and third. So K will take 2. If you have to break down this 18, K will take 2, L will take 8, M will take 8. You have 18. So that's what we're talking about here. Now, let us proceed to quantum numbers. Right now, quantum numbers. The quantum numbers describes the position, energy, and orientation of electrons in an atom. Quantum number describes the position, energy, and orientation of electrons in an atom. There are 4 types of quantum number actually. In chemistry, there are 4 types of quantum numbers. 1, we have the principal quantum number. 2, we have the azimuthal quantum number. 3, we have the magnetic quantum number. 4, we have the spin quantum number. There are 4 types of quantum number in chemistry. The principal quantum number, the azimuthal contour number, the magnetic contour number, and the spin contour number. Don't forget that the contour number describes the position, energy, and orientation of electrons in an atom. That means where is the position of an electron in an atom? The contour number is one that tells us. What energy level does it fall under? Is it level 1, level 2, level 3, or level 4? The contour number helps us. And how is the electron oriented in the shell? The contour number is one that will tell us. Class, so the principal contour number is one that actually tells us the main energy level. The principal contour number helps us to know the main energy level. And class, the symbol for principal contour number is represented by N. The principal contour number is represented by what? N. Now we also have the azimuthal contour number that describes the orbital shape. Who can tell me another name for azimuthal contour number? Drop in the comment section. What is another name for azimuthal contour number? Class, azimuthal contour number is written with L. The magnetic contour number gives the orientation of the orbital in space. And the symbol for magnetic contour number is M. Lastly, we have the spin contour number. The spin contour number describes the direction of the electron spin. And the symbol is MS. Class, very soon you'll find that the electrons can only spin in two directions, either clockwise or anti-clockwise. Electrons can only spin in two directions, either clockwise or anti-clockwise. If you can still hear me, let me know. Let me get the latest report. What's the latest situational report? Can you still hear me? Can you still see the board? Remember, this is an online class, so it's possible that network could have gone. Let us know. Can you still hear me? Can you still see the board? Can you still hear me? Can you still see the board? Good. Omawumi said we can hear you. Yes. Omawumi said we can hear you. Good. Someone says, sir, what about atomic structure? I have taught atomic structure before. I will send the video on the group. I have taught atomic structure before. I will send the video on the group. I have taught atomic structure before. I will send the video on the group. Please take note. Okay, everybody said they can hear me, sir. Thank you for the update. Everybody said we can hear you, sir. Thank you. Let me go and continue. Let me go and continue. Everybody said they can hear me. So, class, the principal contour number is one that shows the energy level. The azimuthal describes the orbital shape. The magnetic shows the orientation of the orbital in space. The spin describes the direction of the electron spin. Well, but that's not all. There's something we must know, class. And before we know that, I have to clean. Class, there's something you must know quickly. That apart from electrons having K, L, M, N, these are the shells that store electrons, shells. But class, are you aware that the shells are not the final point of storage of electrons? Class, as a matter of fact, the shells give rise to what we call orbitals. And the orbitals give rise to what we call blocks. Class, if ever you are asked in the exam, where is the final point of storage, the direct places where electrons are actually stored, is in the blocks. Many students know of the shells, KLMN shells. But class, you must understand that the shells are the ones that undergo configuration to form orbitals. So orbitals are formed from shells. Why do shells undergo configuration to form orbitals? To properly store the electrons. We know we said the electrons can easily be lost or gained. Remember we said the electrons can easily be lost or gained. But the shells now undergo configuration to form orbitals to properly store the electrons. That means the atom is trying as much as possible to not lose the electrons. So the shells undergo configuration to form orbitals. And there are 4 types of orbitals that are formed in chemistry, called s orbital, p orbital, d orbital, and f orbital. So because orbitals are gotten from shells, orbitals are called subshells. Another name for orbitals are subshells. Please stay with me carefully. Follow me carefully. Follow me carefully. Don't forget the storyline that orbitals are originating from shells. Therefore, another name for orbitals is subshells. But class, even the orbitals are not strong enough to store the electrons. So they also undergo configuration and form blocks. So because blocks are formed from orbitals, blocks are called suborbitals. Suborbitals. So class, the s orbital gave rise to the s block, the p orbital gave rise to the p block, the d orbital gives rise to the d block, and the f orbital gives rise to the f block. Now class, you know what's funny? Just like the shells have the number of electrons they can store. Class, the maximum number of electrons that the K shell can store is 2. Maximum electron that L shell can store is 8. M shell maximum is 8. N shell is 18 and above. This is the maximum number of electrons that each shell can store. Are you aware that even the s, p, d, f orbital also have the number of electrons they can take? Class, the s orbital is also called the sharp orbital. Sharp. S stands for sharp. This p orbital is principal. D orbital is diffuse. Another name for D is what? Diffuse. F is functional. These are the 4 names for the 4 types of orbital you have in chemistry. S orbital is sharp orbital, P is principal, D is diffuse, F is functional. As a matter of fact, you could be asked in the exam, what is the shape of the S orbital? Class, the s orbital is spherical in shape. The s orbital has a spherical shape. The p orbital, on the other hand, is a dumbbell shape. The d orbital has a double dumbbell shape. So if this is a dumbbell, then you have another one like this. This is the d orbital for you. But the p orbital is just 1. Why the s orbital? We know what spherical means. Spherical. The f orbital has a complicated shape. It's not. It's unlike what? It's unresolvable. It has a complicated shape. Although some school of thought tells us that it has a multi-dumbbell shape, or complicated shape. These are the 4 orbitals in chemistry. Of course, when you get to university level, there's a 5th orbital called the G orbital. But that's for my university student, that's not for you. For Jamb level, O level, A level, we are told to just teach you S, P, D, F. You know, knowledge evolves. As you're going higher and higher, knowledge keeps going. Knowledge keeps going. But for your level, nobody will ask you in Jamb for G orbital. You should just know S, P, D, F orbital. S orbital is spherical. P orbital is a dumbbell shape. The d orbital is a double dumbbell shape. F is what? Complicated. And these are their names. S is sharp, P is principal, D is diffuse, F is functional. The next thing you need to know is the maximum number of electrons each orbital can take. Just like each shell can take number of electrons, the orbitals also have number of electrons they can take. S can only take 2 maximum. P can only take 6 maximum. It can take less than 6, cannot take more than 6. D is 10 maximum. F is 14 maximum. Same thing for the blocks. 2, 6, 10, 14. I hope we are still together. I hope we are still together. I hope we are still together. Give me a report. Give me a report. Give me a report. Are we still together? Give me a report. Let me give you a little time to write. Let me give you a little time to write. Let me give you a little time to write. Good. Desire said yes, sir. Good, good, good. That means we have a very favorable network today. We have a very favorable network today. Take a while and write so that we can proceed. Take a little while and write so that we can proceed. Take a little time and write so that we can proceed. I'll give you 30 seconds to quickly write so that we can proceed. Good. Kelvin Samuel says, sure, active, sir. Well done. This is the energy. That's good. That is good. That is good. Time to clean now. Sometimes if I'm too fast and I clean the bottle fast, quickly pause and screenshot that part in your phone so you can write it later. Try to be smart. Class, today we're not talking about shells. We want to focus on the orbitals and the blocks. Another thing I want you to know today is that, let's look at the block level. The S block is actually made up of one column, class. The P block contains 3 columns. The D block contains 5 columns. The F block contains 7 columns. One, two, three, 4, 5, 6, 7. Class, each column can only take 2 electrons. Each column can only take 2 electrons. So if the S block contains only one column, it means that you can only take 2 electrons. Each column can only take 2 electrons. This explains why S block can only store 2 electrons. But the P block has 3 columns. Each column can take 2 each. So 2 times 3 will give you 6. The D block has 5 columns. Each can take 2. So 5 times 2 will give you 10. The P block has 7 columns. Each column can take 2 electrons. So 7 times 2 you have 14. This explains why the S block can store maximum of 2 electrons, the P block can store maximum of 6 electrons, the D block can store maximum of 10, and the F block can store maximum of 14 electrons. Class, notice that even when I'm putting the electrons inside the block, I am still not, look at you, notice that one electron is facing up and one is facing down. This is due to Pauli's exclusion principle in chemistry. Pauli's exclusion principle. Class, according to Pauli's exclusion principle, an electron can have the same principle, the same azimuthal, the same magnetic, but when it comes to the spin, class, the spin is the major differentiator. Remember I said we have 4 types of quantum number: principal quantum number, azimuthal quantum number, magnetic quantum number, and spin quantum number. According to Pauli's exclusion principle, the spin is one that differentiates one electron from the other. No 2 electrons can have the same spin. Class, in a block, once one electron is facing up, the other must face down. What this principle is telling us that no 2 electrons can face the same direction. Class, it is wrong in chemistry to have 2 electrons facing upward. Very wrong. If one is up, class, upward means clockwise, down means anti-clockwise. So electrons can spin in 2 directions. Up means clockwise, down means anti-clockwise. Up means clockwise, down means anti-clockwise. Please take notes. So class, never put two electrons in the same orientation. If one is facing up, one must face down. Class, we have another rule called Abel's rule. Abel's rule. Class, it is Abel's rule that tells us that when filling electrons in orbitals, we start by filling electrons from the orbitals of lower energy level before we get to those of higher energy level. When filling electrons in orbitals, we start by filling what? Orbitals of lower energy level before those of higher energy level. Class, it is wrong to start filling from high energy before low energy. Start from the low energy before you get to high energy. Whose rule is that? Abel. In chemistry exam, if you are asked, what's another name for Abel? Abel means energy. Another name for Abel, the synonym for Abel is energy. Let's keep going, let's keep going. The synonym for Abel is energy. Class, let us now show you the different orbital energy level in chemistry. Let us show you the different orbital energy level in chemistry. Class, the lowest orbital energy level is 1s. After 1s, you have 2s, then you have 2p. Then you have 3s, then you have 3p, then you have 3d. Then you have 4s, then you have 4p, then you have 4d, then you have 4f. Then you have 5s, 5p, 5d, and 5f. 6s, 6p, 6d, and 6f. Class, it still continues, but let's stop here because this can take care of a lot of elements already. Class, I will show you the arrow at which the energy level comes. This 1s. So you are following Abel's rule. When you want to fill electrons in an orbital, start from 1s. Once 1s is filled up, you go to 2s. Once 2s is filled up, you come to 2p, then 3s. Then 3p, then 4s. Then 3d, 4p, 5s. Then 4d, 5p, 6s. Then 4f, 5d, 6p. Then 5f, 6d, then 6f. Class, these are the energy level. This is how you should start filling electrons. And I'll give you an example soon. I don't want to be too fast. I want you to actually understand today's class very well. So pay close attention. Pay close attention. Pay close attention. Hope you are writing material. This is a very serious class. Pay close attention. Pay close attention. So you can see 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, 6p, 5f, 6d, 6f. So let us assume that someone asks you to write down the SPDF configuration of sodium, which is number 11. Because the atomic number of sodium is 11. I've already taught our students the first 20 elements and how to determine atomic number and atomic mass. If you miss the class, don't worry yourself. I will repost the video after this class on our chemistry private group. I will post the video. If you're on our chemistry private group, those that are paid, you get the video. Are we together? Of how I thought, I broke down the first 20 elements, thought out of no atomic number, atomic mass, everything. I've taught it very well. For class, sodium is number 11 electrons, and you have to write down the SPDF configuration for sodium. So you want to fill the 11 electrons of sodium in their orbitals, in the SPDF orbital. Now, according to Abel's rule, when you want to fill electrons in the orbitals, start filling from lower energy level. So 1s is the lowest energy level. So you want to write down the configuration of sodium. You're going to say 1s. How many electrons can you store in an s orbital? 2. Remember, s can only take 2 maximum. Don't forget. After filling 1s, according to Abel, move to 2s. But 2s, anything s orbital can take only maximum of 2 electrons. Whether you are 1s, whether you are 2s, everybody under s can only store 2 electrons maximum. Everybody under p, whether you are 2p, 3p, 4p, can only store what? Maximum of 6. They can take less than 6, but cannot take more than 6. Everybody in the D family can take maximum of 10, cannot take more than 10. They can take less than 10. Even if not up to 10, they will take. But their maximum is 10. Everybody in the F family, maximum is what? 14. But they can take less than 14. So please take note. So when filling electrons in orbitals, you fill from lower energy level. Look at the arrow. 1s first, then 2s, then come to 2p before 3s, then come to 3p before 4s, 3d, 4p, 5s. These are you fill electrons in orbitals. So we want to fill 11 electrons of sodium in orbitals. The first 2 will go to s, 1s, The next 2 will go to 2s. After 2s, the next energy level is 2p, following the Abba's rule. Fill from lower energy level before higher energy level. Always fill from lower energy level before higher energy level. So 2p is there, but don't forget that p can take up to 6 electrons. So 2p 6. Don't forget we are going to 11. So don't go and overfill. You are going to 11 electrons. Let us count how many electrons have been filled so far. 2 plus 2 is 4. 4 plus 6 is 10. Remaining only 1 electron left. After 2p, what's the next energy level? 3s. So this 3s will take what? 1. Class, this is how we get the electronic configuration for sodium. This is how we get the SPDF electronic configuration for sodium. If we have to do for any other element, let us do for, what if you ask to write, okay, let us do for sulfur 16. The atomic number of sulfur is 16, meaning that it has 16 electrons. Sulfur contains 16 electrons. And we want to write the SPDF configuration for sulfur. Sulfur 16. Notice I wrote the 16 below. Why? Because atomic number is written below. What is written above here is atomic mass. This number above is atomic mass. That's why I said I've taught atomic structure before. Talking about atomic mass, atomic number, all those things. Please, there's a video for it. I'll send it. So class, sulfur is 16. Let's write the SPDF configuration for sulfur. You are trying to fill 16 electrons. Start from 1s. 1s2. After 1s2, you go to 2s2. After 2s2 is next, 2p, 6. How many have you filled so far? So you don't go and overfill. 2 plus 2, 4. 4 plus 6 is 10. Remaining 6 electrons to fill. After 2p is 3s. S can take only 2. We still have 4 electrons left to fill. We're going to 16. After 3s is 3p. The remaining 4 electrons will be in the 3p shell. Class, this is the SPDF configuration for sulfur. If you use this approach, you can write the configuration for any element. Any what? Element. But class, there are some things I must teach you now. Class, sometimes they can ask you to write the noble gas configuration. Class, they can ask you to write the noble gas configuration for sodium. Class, even if this is 1s2, 2s2, 2p6, 3s1, you could be asked in the exam to write the noble gas configuration. What is the noble gas configuration for sodium? Class, you are going to ask yourself, what is the closest noble gas to sodium? What is the closest noble gas to sodium? If we list our first 20 elements here, hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, argon, potassium, calcium. In our first 20 elements, before this is number 1, number 2, every element has a position. Number 3, 4, 5, 6, 7, 8, 9, 10. Class, sodium is number 11, magnesium is 12, 13, aluminium 14, silicon 15, phosphorus 16, sulfur 17, chlorine 18, argon 19, potassium 20, calcium. Class, neon is the closest noble gas. In case they're just joining us, I've taught our students about the noble gases. But if you're somehow good in chemistry from secondary school, you should still be able to catch up because they've taught you in secondary school. Who are the noble gases? They are the what? Inert or rare gases among the elements. They are the ones that have stable configuration. The noble gases are known for their stable configuration. Class, I want to teach you how to write the noble gas configuration of sodium. Class, this is the normal SPDF configuration of sodium. But in the exam, they can ask you to write the same configuration in terms of the closest noble gas to sodium. It's called noble gas configuration. It's called what? Noble gas configuration. Noble gas configuration. Class, who is neon? Neon is number 10. And neon is a noble gas. Class, when they ask you to write the noble gas configuration of an element, you will find the closest noble gas to the element. Who is the closest to sodium? Neon. When I mean closest, that means the closest noble gas before the element, not the closest one after the element, before the one that comes before the element. In case you're not very familiar with noble gases, these are noble gases in the first 20 elements: helium, neon, and argon. These are the noble gases. So number 2 element is a noble gas, number 10 element is a noble gas, number 18 element is a noble gas. Class, what would have been the SPDF configuration for neon if it has 10 electrons? Let us try to store the 10 electrons of neon in the SPDF about row. Class, remember you start from the lower energy level, right? You're going to say 1s, 2, s can take only 2. After 1s, you come down to 2s, 2s, 2. After 2s, you come down to 2p, 2p. P can take how many? 6. Remember that p can take up to 6 electrons. So 2 plus 2 is 4, 4 plus 6 is 10. So you have 1s2, 2s2, 2p6. This is the configuration of neon. Class, I now want to write the noble gas configuration for sodium. Notice that this is 1s2, 2s2, 2p6. This first part of the configuration of sodium is the same with neon. 1s2, 2s2, 2p6. 1s2, 2s2, 2p6. Class, I'm going to replace 1s2, 2s2, 2p6 with neon and bracket it. And who is left? 3s1. Class, this is the noble gas configuration for sodium. This is the noble gas configuration for sodium. It is when you replace most of the configuration with the closest noble gas to the element and write what is left. So this 1s2, 2s2, 2p6 is the same configuration for neon, 1s2, 2s2, 2p6. So replace everything here with neon and what's left? 3s1. So neon 3s1 is the noble gas configuration for sodium. Class, we can do the same thing for sulfur. Look at 1s2, 2s2, 2p6 is neon. So that will be neon 3s2, 3p4. This is the noble gas configuration for sulfur. I hope you are still with me. I hope you are still with me. If you are still with me, say, sir, we are with you. If you are still with me, if you can still see the board, if you can hear me, say, sir, we can hear you, we can see the board. If you can still hear me and you can see the board, say, we can hear you, sir, we can see the board. Good, 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 good. I hope you are learning something. I hope you are learning something. Let us keep going, let us keep going. Class, let us now write the configuration for someone like calcium. Calcium is number 20. In the element table, calcium is number 20. If we are trying to configuration for calcium, well, we're trying to store 20 electrons. Start from 1s, 1s2, after 1s go to 2s, 2s2, after 2s go to 2p, 2p6, after 2p go to 3s, 3s2, after 3s go to 3p, 3p6, we are going to 20, don't forget yourself. After 3p go to 4s, 4s2. I think this is 20 now, 2 plus 2, 4, plus 6, 10, 12, 18, 20. This is the configuration of calcium, class. But in terms of a noble gas, who is the closest noble gas to calcium? It's argon. Argon is 18. So class, we are going to account for the first 18 electrons in calcium and replace them with argon. 2 plus 2, 4, 4 plus 6, 10, 12 plus 6 is 18. So class, this is argon. So we are going to say, replace with what? Argon, and then what's left? 4s2. This is the noble gas configuration for calcium. Are you getting something? This is the noble gas configuration for calcium. This is the noble gas configuration for calcium. Thank you, Kelvin. Kelvin says, sir, we can hear you and we can see the board. Thank you for updating me, Kelvin. This is the noble gas configuration for calcium. Yes, Kelvin, thank you. Desire, thank you for updating me. Desire said, go on, sir. Desire said, go on, sir. That's the energy. That's the energy. Yes. Now, class. Let us now look at someone like, what if they gave you, ask you to find the configuration, SPDF configuration for someone like P3 minus, phosphorus 3 minus. Like, this is not normal phosphorus. This is not normal phosphorus. Phosphorus 3 minus, write down the SPDF configuration. Class, who is phosphorus on the element table? Phosphorus falls on number 15. Phosphorus is number 15. Look at phosphorus here. Class, in chemistry, when you see this minus sign in chemistry, when you have a minus charge on you, it means that you have gained electron. But when you have a positive charge, it means you have lost electron. Class, I know it's very funny, because how can someone be having minus and say you have gained? Minus should usually mean that you have lost. But chemistry, when you have a negative charge, it means you have gained electron. When you have a positive charge, it means you have lost electron. So class, P3 minus means that phosphorus has 3 extra electrons. So the normal phosphorus is 15. But this 3 minus means 15 plus 3, which is 18. So when writing the configuration for P3 minus, you're not writing for 15 electrons, you're writing for 18 electrons because it's P3 minus. But even if they just ask you for normal phosphorus, you're writing for 15 electrons. Let me not be too fast, let me calm down. If they ask you for normal phosphorus, you're writing for 15 electrons. But if they ask you for P3 minus, charged phosphorus, you are writing for 18 electrons because 3 minus means that you're going to add extra 3 electrons to the normal electrons for phosphorus. You're going to add extra 3 electrons to the normal electrons for phosphorus. So phosphorus normally has 15 electrons. Look at it in element table 15. But P3 minus means that phosphorus has gained 3 extra electrons. So don't go and rush and still write for 15. Some people will rush under exam tension, forgetting that this 3 minus is there. You're supposed to be writing for 18. So we're trying to store 18 electrons, even if phosphorus has 15. We're trying to store 18 because of this 3 minus charge. This 3 minus charge means phosphorus has gained extra 3 electrons. So we're writing for 18 electrons, class. So let's start writing from the lowest energy level, 1s2, 2s2, 2p6, 3s2. Class, the time will come, you will no longer need this table. If not, I was teaching. I don't need this table to write SPDF configuration because I'm teaching you, that's why. But after a while, but when I first learned this when I was a student, then I was also using the table. But after a while, I stopped opening the back to check because you just learn by what? When you repeat a formula over time, it just sticks to you, right? Yeah, so don't worry, you get it. Just keep practicing. Take a lot of questions. Practice makes perfect. So 1s2, 2s2, 2p6, 3s2. We are going to 18, don't forget. After 3s2, 3p6. I think this is 18. 2 plus 2 is 4, plus 6, 10, 12, 18. Class, this is the combination for P3 minus. But some students will go and write for normal phosphorus. If it was normal phosphorus, it would have been 1s2, 2s2, 2p6, 3s2, 3p, 4, 15 electrons is 3p3, 3p3. So class, please take note of this. The same thing also applies if they ask you to write the SPDF configuration for Mg2+, magnesium 2+. Write the SPDF configuration for magnesium 2+. Class, when you see magnesium 2+, it means that this magnesium is not a normal magnesium. In chemistry, when you have a positive charge, it means you have lost. When you have a negative charge, it means you have gained. Please take note. When you have a positive charge, it means you have lost. When you have a negative charge, it means you have gained. Class, this positive 2 means that magnesium has lost 2 electrons. So we need to ask ourselves, how many electrons does normal magnesium have? 12. From the table, magnesium usually has 12 electrons. But 2 plus means that magnesium has lost 2 electrons, meaning that we are writing for 10 electrons. Because 12 minus 2 is 10. So when writing a configuration for Mg2+, you're writing for 10 electrons. That's 1s2, 2s2, 2p6. 1s2, 2s2, 2p6. Please take note of these things. Please take note of these things. Class, the next thing I want us to look at now is Ohm's rule of maximum multiplicity. But before we do that, something I should have told you quickly. I should have told you that quickly. This is 3p, this is 3d, this is 4s, 4p, 4d, 4f, 5s, 5p, 5d, 5f, 6f, 6p, 6d, 6f. Let me show you something quickly. Class, quickly write down stability of orbitals. Stability of orbitals. Write down in your book. Stability of orbitals. 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 Now, right, note, orbitals are stable when they are filled completely with 2 electrons in each block. With 2 electrons in each block, or when they are filled singly. Or when they are filled singly with 1 electron in each block. Or when they are filled singly with 1 electron in each block. Orbitals are stable when they are filled completely with 2 electrons in each block, or when they are filled singly with 1 electron in each block. I'll explain. Class, don't forget that we have S orbital has only 1 block, P has 3 blocks, don't forget. D contains 5, F contains 7. Remember I told you this. Class, stability of orbital rule tells us that orbitals are stable when they are filled singly, when they are filled completely with 2 electrons in each block, or when they are filled singly with 1 electron in each block. Class, I want you to take note that if you put 1 electron in a block, it is stable. If you put 2 electrons in a block, also stable for S or block. Look at this P block. If you put everybody 1, 1, 1, stable. Or if you feel it, everybody has 2, 2, 2, stable. But class, let me tell you an orbital that is not stable. An orbital is not stable when some people have 2 and some people have 1. This is not stable, not stable. For orbitals to be stable, it's either everybody has 1, 1 in their block, or 2, 2 complete in their block. A mixture of 2 and 1 is an unstable orbital. Class, if this d orbital should be stable, it's either everybody has 1, 1, 1, 1, 1, then we are all good. Or everybody must have 2 complete. Then we are all good. What we don't want is when some people have 2 and some people have 1. Those kind of orbitals are not stable. That's what the principle of stability of orbitals is telling us. If you understand, say sir, I understand in the comment section. If you're still with me, remember we say we will not live till the end. If you are still with me, say sir, I understand, sir, I am getting you. Sir, I understand, sir, I am getting you. If you are getting me, say sir, I am getting you, I understand. If you are getting me, say sir, I understand, I am getting you. Sir, I understand, I am getting you. I've just taught you stability of orbitals now. What is the importance of this? Because class, in your exam, they could ask you a very, very interesting question. To write down the SPDF configuration of 2 special elements. We want to look at chromium and copper. Class, I want you to also note that S orbital is always stable as long as there is an electron inside. S orbital is always what? Stable, because it has only 1 block. So once you put 1 inside, it's stable. If you still put 2 inside, it's stable. The only time an S orbital is not stable is if there is no electron inside at all. S orbital is always stable, whether it is filled singly or paired. S orbital is always stable, whether it is filled singly or paired. Class, in the exam you could be asked to write the electronic configuration of chromium. Chromium is number 24 and copper is number 29. Class, there's a reason why I taught you stability of orbitals. I want to show you something now. I just told you that S orbital is always stable, right? S orbital is always, whether it is 1 electron or it is 2, it is stable. The only reason when S is not stable, if there is no electron inside, then it's not stable. When there is no electron inside, it's not stable. If there is at least 1 electron, it is stable. Let us write the SPDF configuration for chromium, class. You're going to have, from the lowest energy level, don't forget, 1s2. We are going to 24. Chromium is 24. 2s2, 2p6, 3s2, 3p6, 4s2, 3d4. Because after 1s is 2s, after 2s is 2p, 3s, 3p, 4s, then 3d is next. If you're looking at the arrow, the energy level, 3d is next. Class 3d4. This is what every normal science student will write, but you are wrong. This is what every normal science student will write in the exam, but you are wrong. Class, why are you wrong? Because there's something quiet that happens in the electronic configuration for chromium and copper that not all chemistry students are aware of. Class, remember I told you, let us look at this last orbital of chromium, which is D orbital. It has 4 electrons. Let us break it out, 4 electrons. Don't forget that D has 5 blocks. So 4 electrons means 1, 2, 3, 4. Class, there's a rule I'm following here when filling electrons in orbital. It's called Hund's rule. Hund's rule of maximum multiplicity. Hund's rule of maximum multiplicity. Hund's rule. Hund's rule of maximum multiplicity. Class, according to Hund's rule of maximum multiplicity, when filling electrons in blocks or orbitals, we fill singly before pairing. What does it mean? We must first give everybody 1 before we start pairing. Class, this is a D block again. This D block is carrying 4 electrons. It's very wrong for me to put 2 here when others have not even gotten 1 yet. So according to Hund's rule, class, of maximum multiplicity, you start giving everybody 1. When 1 has gone around, you now start pairing if it still remains. But you can see even the 1 did not go around because we have 1, 2, 3, 4. This guy does not have any electron because there are only 4 electrons, 3d4. But class, with 1 more electron in this block, this D block will be very stable. Don't forget, stability of orbitals. The orbitals are stable when they are filled singly or when they are completely filled 2. But this D block is lacking 1 more electron, class. What happens is that this S orbital will transfer 1 electron to this D block. Why? Because even if you remove 1 from S, S is still stable. I told you, S orbital is always stable. S orbital is always stable. Whether there's 2 or there's 1 inside, S is always stable. Whether there's 2 is stable, if it's 1 is still stable. S orbital is always stable, class. So, class, S orbital will transfer, there was 2 here before, don't forget. They will now remove 1 and transfer here, and this guy becomes 5. So that this guy can be stable. To ensure the stability of the D orbital, there will be a transfer of 1 electron from the S orbital to the D orbital. And the D orbital is now stable. And the electronic configuration of chromium is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d5. But if you follow the normal rule, you have written, a normal chemistry student that has not been taught well, we have written 4s2, 3d4. I can assure you this, the wrong option will be in your option in the exam. Plus, in case you didn't understand this, let us look at copper, because the same thing happens in copper. Look up. Copper is number 29 elements. It means it has 29 electrons. Let us start filling the number of electrons in copper. I'm going to have 1s, some lower energy level, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d9. Class, let's revisit this 9, this D. D block is 5, right? Has 5 blocks. 1, 2, 3, 4. 1, 2, 3, 4, 5. And this D has 9 electrons to be filled. Now, following Hund's rule of maximum multiplicity, what did I tell you? You first start filling singly. So you have 9 electrons to fill, but give everybody 1 first. Fill singly before pairing. You have filled 5, remainder 4 to make 9. Now start pairing. Start pairing, start pairing, start pairing. Class, this last block is needing 1 more electron. And if you put 1 more electron here, this block will be very stable. Because blocks or orbitals are stable when they are filled singly or when they are paired. I just taught you that in stability of orbitals. What happens is that this S block will be magnanimous enough to say, no, I can give you 1. Because even if I lose 1, it doesn't affect me. And this S will shift to 4s1, and this guy will turn to 10. And there's 1 more electron here. To ensure the stability of the copper. If you understand and you are following me, say, sir, I am with you. Say, sir, I am with you. If you are still following, say, sir, I am with you. If you are still following, say, sir, I am with you. If you are still following, say, sir, I am with you. Let me know in the comments. If you are still following, say, I am with you, sir. Where's my first comment? Where's my first comment? I am with you, sir. Where's my first comment? I am with you, sir. Are we together? Are we together? Are we together? Thank you, Kelvin. Thank you, Kelvin. I almost thought the network has gone. Okay, that means we are together. Thank you, Kelvin, for always updating us. Thank you. I almost thought the network has gone. That means we are still together. That means we are still together. Now that I have understood this and I've also done on through, the next thing we need to look at now is how to calculate number of unpaired electrons. Class. Number of unpaired electrons. Number of unpaired electrons. Class, you could be asked to calculate the number of unpaired electrons. Number of unpaired electrons in the atom of an element. Number of unpaired electrons. Number of unpaired electrons, class. Class, you could be asked to calculate the number of unpaired electrons in the following elements. In the following elements. One, nitrogen. Two, phosphorus. Three, let's look at carbon. How do you calculate number of unpaired electrons? How do you calculate the number of unpaired electrons? Class, you must first write down the SPDF configuration. Class, what number does nitrogen fall when listing the elements? Nitrogen is number 7. Phosphorus is number 15. Carbon is number 6. Now, so we're trying to write for 7 electrons, right? This 1s2, 2s2, 2p, 2 plus 2 is 4, 2p3. 2p what? 3, because nitrogen is number 7. So 2 plus 2 is 4. It means that only 3 electrons are left and they will enter the p orbital. Yes, p can take 3, can take up to 6, right? Now class, we're now going to focus on this last orbital of the configuration. P, how many blocks does P have, class? P has 3 blocks. Now when you want to fill the electrons inside this, you fill singly before pairing, don't forget. So we have only 3 electrons to fill. So this is 1, 2, 3. Now, the electrons are finished. You now ask yourself, how many electrons are unpaired? Class, unpaired means that how many electrons are standing alone? Normally, electrons should be 2, 2 in pairs. How many electrons are standing alone? You have 1, you have 2, we have 3. These 3 electrons are standing, they are not paired with the second base. So class, it means that nitrogen contains 3 unpaired electrons. Nitrogen contains 3 unpaired electrons. In case you did not get this, before we finish the 3 examples, you get it. Before we finish these 3 examples, you get it. Let's go to phosphorus 15. Phosphorus 15. So before we do that, we'll write the configuration first. What's configuration of phosphorus 15? 1s2, 2s2, 2p6, 3s2, 3p, 2 plus 2 is 4, 4 plus 6 is 10, this is 12, this 2 plus 2 is 4, plus 6 is 10, 12, we are going to 15, 12 plus 3 is 15. Class P3 definitely means that phosphorus also contains 3 unpaired electrons, because you bring out a p block, p contains 3 blocks. This is 1, 2, 3. You feed the electrons 1, 1. Give everybody 1, 1 first, remember. So you are filling 3 electrons in the p block. So when you want to find number of unpaired electrons, you have no business with all these guys. It's the last person on the configuration. So if you cannot write SPDF configuration, you will not be able to find number of unpaired electrons well. Because to find number of unpaired electrons, you must first write down the configuration out and focus on the last orbital. Then draw out the block. If it's an S block, it means it's one block you will draw. If it's a P block, it's 3 blocks. If it's a D block, it's 5 blocks you will draw. If it's an F block, it's 7 blocks you will draw. That's why I started this class by teaching number of blocks that each orbital has. Good. So P also contains 3 unpaired electrons. But these 3 electrons are unpaired. These 3 electrons are what? Unpaired. 3 unpaired electrons. Class, note that anytime an element contains unpaired electrons, it will exhibit magnetic property. The elements that have unpaired electron exhibit what? Magnetic properties. That means they have high potential for magnetism. Elements that what? Contain one or more unpaired electron have high what? Tendency to be magnetic. In fact, they are called paramagnetic atoms. So an atom can either be paramagnetic or diamagnetic. An atom can either be paramagnetic or diamagnetic. A paramagnetic atom is an atom that what can exhibit magnetic features, magnetic properties, due to its number of unpaired electrons. Let's look at carbon. Carbon is 6. 1s2, 2s2, 2p2. Because 2 plus 2 is 4, 4 plus 2 is 6, 2p2. It falls on the P block, so we're going to say 1, 2. You have only 2 electrons you are filling. So carbon contains 2 unpaired electrons, class. If you have understood now, say, sir, okay, I understand now. Sir, okay, so you first write down the electronic configuration, then focus on the last person, bring out this block, and arrange the electrons inside. And find out how many electrons are paired, how many electrons are unpaired. That's just the whole concept, class. That is the whole concept. 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 If you have to find number of unpaired electrons for someone like fluorine, fluorine is 9. 1s2, 2s2, 2p5. 2 plus 2, 4. 4 plus 5, 9. 2p5. Now P is the one you focus on. Leave these other guys, focus on this guy. P contains 3 blocks. Fill singly first before pairing. Fill singly, then start pairing. You stop at 5. 1, 2, 3, 4, 5. Only 1 unpaired electron. Fluorine has 1 unpaired electron. Fluorine has 1 unpaired electron. Are we still there? Are we still there? Fluorine has 1 unpaired electron. Let's keep going, let's keep going, let's keep. So class, this is how you solve for number of unpaired electrons. This is how you solve for number of unpaired electrons. Let's now go to isoelectronic ions. Write down isoelectronic ions. Isoelectronic ions. Isoelectronic ions. These are ions that contain the same number of electrons. Class, they could be ions, they could be atoms. As long as they have the same number of electrons, isoelectronic ions or atoms. These are ions or atoms containing the same number of electrons, class. When ions or atoms contain the same number of electrons, they are called isoelectronic. Example, you could be asked in the exam, which of the following ions or atoms and is not isoelectronic? Which of the following? Ions or atoms is not what? Isoelectronic. A, we have neon. B, we have Mg2 plus. C, we have Na plus. D, we have O2 minus. And E, we have K plus. Which of the following ions or atoms is not isoelectronics? Class, we need to ask ourselves, how many electrons does neon have? Neon has 10 electrons. Because neon falls on number 10 of the periodic of the element table. 10 electrons. Magnesium has 12 electrons normally. But 2 plus means it has what? Lost. In chemistry, when you are plus, you have lost. 2 plus means it has lost. So 12 minus 2, 10 electrons. So isoelectronic, isoelectronic. Sodium has 11 electrons normally, but plus 1 means it has lost 1. When you are plus, you have lost. So 11 minus 1, 10 electrons. Oxygen normally has 8 electrons, class. If you list the first 20 elements, oxygen falls on number 8. But 2 minus means it has gained. When you are minus in chemistry, means you have gained. You have gained 2 electrons. 2 minus means it has gained 2 electrons. So 8 plus 2, 10 electrons. Isoelectronic. Iso. Now let's go to potassium plus. Potassium is number 19 on the element table. But plus 1 means he has lost 1. In chemistry, when you are plus, you have lost. 19 minus 1 is 18 electrons. This guy is not isoelectronic with the others. This guy is not isoelectronic with the others. The others are isoelectronic because they contain the same number of electrons. They contain the same number of electrons. Are we gaining something? Are we gaining something? I hope we are gaining something in today's class. Someone says, sir, how is carbon 2 unpaired? How is carbon having 2 unpaired electrons? Well, carbon is number 6 on the element table, which is 1s2, 2s2, 2p2. Focus on this p. P has 3 blocks. Look at it. And you have only 2 electrons you are filling. So fill 1 and 2. So only these 2 electrons are unpaired. There's nothing here to say is unpaired. Now you cannot say this is unpaired. Class, if there's no electron in the block, it is not unpaired though. There must first be electron before you now say it's unpaired. There's not even electron here at all. So it's only these 2 that are unpaired. There's no electron here at all. So 2 unpaired. Please take note. 2 unpaired. Don't forget, I will not live till the end. 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 Someone said Omo. You are seeing real work now, B. Someone said Omo. That's real work, serious work. I will not live till the end. So these are isoelectronic ions for you. The next thing we want to look at is we want to break down the principal, which is L, azimuthal. I want to look at orbital designation. Orbital designation. Class, remember we did quantum number. We say L represents principal. Sorry, N represents principal. N is principal. L is azimuthal. I was asking you guys what's the name for azimuthal quantum number. It's called subsidiary quantum number. Please take note. Another name for azimuthal quantum number, they can ask you exam is subsidiary. Another name for azimuthal quantum number is subsidiary quantum number. We have M, which is magnetic. And we have MS, which is spin quantum number. Class. The principal quantum number represents the number of shells. So class, the value starts from 1, 2, 3, like that. So a principal quantum number cannot be 0. It was 1, 2, 3, because number of shells, you cannot have 0 shells. Now you are not an atom. At least the least element has 1 shell. So the principal quantum number is what? Starts from 1, 2, 3. Now the azimuthal quantum number class is usually one number less than the principal. So azimuth L, the symbol for azimuth is L, is N, which is principal, minus 1. The azimuth is always one number less than the principal. So class, if the principal is 1, the azimuth is 1 minus 1, you have 0. If the principal is 2, azimuth is 2 minus 1, you have 1. If the principal is 3, azimuth is 3 minus 1, you have 2. So class, azimuth can start from 0, 1, 2 and keep going. Now what of the magnetic class? Class, the magnetic quantum number also depends on the azimuth quantum number. As a matter of fact, the magnetic quantum number ranges from minus L to plus L. That is from minus value of the azimuthal to positive value of the azimuthal. So if someone tells me that my azimuthal quantum number is 0, my magnetic will be from minus 0, all numbers from minus 0 to plus 0. But of course, that's still 0. So when L is 0, my M is also 0. When your azimuthal is 0, your magnetic is also 0. But it's no number like minus 0 and plus 0. 0 is 0. 0 is what? 0. But class, when your azimuthal is 1, your magnetic ranges from all numbers between minus 1, 0, and 1. When your azimuthal is 2, your magnetic ranges all numbers from minus 2 to positive 2. Remember, minus L to plus L. So minus 2, minus 1, 0, 1, 2. When your azimuthal is 3, your magnetic is what? Minus 3, minus 2, minus 1, 0, 1, and 2. Class, this is very, very, very important you know it. Class, like I said, the principal talks about the shell. The azimuthal tells about the orbital or designation. Class, the value your azimuthal quantum number can allow me to know what orbital the electron is stored in. Class, when L is 0, it means that we're dealing with an S orbital. Don't forget, I'm teaching you orbital designation. When the azimuthal is 0, just know you're dealing with an S orbital. When the azimuthal is 1, you're dealing with a P orbital. When azimuthal is 2, you're dealing with a D orbital. When azimuthal is 3, you're dealing with an F orbital. Please take note. Because you could be asking the exam, I'll give you questions, don't worry, you see. I'll give you questions, don't worry, you will see. That was the orbital designation. When they ask you to find orbital designation, and they give you some set of what? Quantum numbers. What will you do? I'll give you questions so you see. Make sure you're writing. Okay, so class, the spin quantum number is different from this other three. I told you these three could be the same, but this spin is always different. This spin quantum number just tells us how is the electrons oriented in the block. Now, this spin can either be clockwise. How do we represent clockwise? Plus 1 over 2. Or anti-clockwise. How do we represent anti-clockwise? Minus 1 over 2. So class, anytime you see plus 1 over 2 for spin, MS, just know that the electron is clockwise. That is facing up. Then the electron is facing what? Up. When the electron is facing down, it's anti-clockwise, minus 1 over 2. That's the sign. That's the sign we use for spin quantum number. That's the sign we use for spin quantum number. Clockwise is upward, anti-clockwise is downward. So there are only two things for spin quantum number. Either you are clockwise or anti-clockwise. The spin quantum number does not do much. It just tells us the orientation of the what? Electron in the block. Is it facing up or is it facing down? If it is facing up, we call it clockwise, plus half. If it's facing down, anti-clockwise, minus half. Please take notes. Please take notes. Class, as I've told you, that when L is 0, L means the azimuthal quantum number, right? L means the azimuthal quantum. When L is 0, I deal with an S orbital. When L is 1, is a P orbital. When L is 2, a D orbital. When L is 3, an F orbital. Please take notes. So they can ask you in the exam, what is the orbital designation? For an electron in an atom with the following quantum number. What is the orbital designation for an electron in an atom with the following quantum number? L is 2, sorry, not L, N is 3, and L is 1. When N is 3 and L is 1. So don't forget that N represents the principal, while L represents the azimuthal. When N is 3 and L is 1, class, what is the orbital designation? Class, orbital designation is 3, because you start with the N, 3. L, when L is 1, what does it mean? P. So, I mean that the electron is in the 3p orbital. The electron is in the 3p orbital. Where did I get 3 from? The principal. Remember that every orbital has a shell number. Even when I was doing that thing, 1s, remember that thing we did 1s, 2s, 2p? Check, S and P never stand on their own. They always have a number beside them. That number beside them is the principal number. 3S, 3P, 3D. No orbital stands on its own, just S, P, D, no. They have things that are behind them. That's the principal. 4S, 4P, 4D. Didn't you wonder where is all this number coming from? This number represents the shell that's carrying the orbital. Remember when I started this class, I told you that shells give rise to orbitals. Don't forget. Shells is the one that forms orbitals. It is shells that give rise to orbitals. That's why orbitals are called what? Sub-shells. Orbitals are called sub-shells because shells are the ones that give rise to orbitals. That's why orbitals cannot just stand on their own. You can't just see S, P, D, F. There's a number beside it. This is 1S or 2P or 3D. You understand? This number beside it represents the shell that formed the orbital. The number beside every orbital shows the shell that produced that orbital. Every orbital was produced from a shell. Why was orbitals formed? Because shells were not capable enough of storing the electrons. Electrons were easily lost. So shells now undergo configuration to say, let us form orbitals. Orbitals also undergo configuration to form blocks. So the final point of storage of electrons, actually the blocks in chemistry, we had asked, the final point of storage of electrons is the blocks. So class, orbitals can exist on their own as just S, P, D, and F. There's a number beside them. The number beside them shows the shell level that formed the orbital. So what they told you now in this question, what is the orbital designation for an electron and atom? With the following quantum number, when n is 1, n means 1, when n is 3, means that this person was formed from the third shell, because n represents principal quantum number. And principal quantum number deals with the shell level, right? The shell level. What shell does it form? 3. Now, L is azimuthal. Azimuthal talks about the orbital level. Azimuthal talks about the orbital level. Look at it. When L is 1, it means we're dealing with a p orbital. So this is 3 but p. That's the answer to this question. 3p. 3p. Let me give one more question to be sure that you're following. Same question. What is the orbital designation for an electron and atom with the following? When n is 2, or let's say when n is 4 and L is 2. When n is 4, when n is 4 and L is 2, can tell me the answer in the comment section. Tell me the answer in the comment section if you are following me. When n is 4 and L is 2, what is the orbital designation? When n is 4 and L is 2, it's going to say 4. When L is 2, what do you have? D. So you're going to 4D. So the orbital designation here is 4D. Class, this is quantum number for you and orbital designation. Let us quickly go to periodic table. Let us quickly go to periodic table. We are supposed to do quantum theory, atomic structure, and periodic table. We have looked at atomic structure before. We've just finished quantum theory and quantum number and SPDF configuration. Now let's go to periodic table. Let us round up with periodic table. Let us round up with periodic table. Class, we all know that the person that discovered the periodic table is Dmitry Mendeleev. A Russian scientist known as Dmitry Mendeleev. In case you asked in the exam, is the one that is credited with founding of the periodic table. I hope you are still with me. I hope you are still with me. I hope you are still with me. Good. Someone said 4D. It means you are still following. That means you are still following. The person credited with the periodic table is what? Dmitry Mendeleev. That means you're still with me. Good. So you can still hear me well and you can still with me. Good. Let's look at the periodic law. What does the periodic law say? Right, and the periodic law states that. The periodic law states that. The periodic law states that properties of elements are a periodic function of the atomic numbers. Properties of elements are a periodic function of the atomic numbers. Properties of elements are a periodic function of the atomic numbers. The periodic law states that properties of elements are a periodic function of the atomic numbers. Are a periodic function of the atomic numbers. That means we arrange elements in the periodic table based off of the atomic numbers. Based off of the atomic numbers. Class, why do we need the periodic table? Why do we need the periodic table? Because we have so many elements in chemistry. We need to be able to factor them into families and groups. Okay, let us know. When we see these elements, okay, these are how they behave. This particular element, these are how they behave. Okay, these are how these guys behave. These are how these guys behave. Super, super important, you know that. Class, you're lucky that in your Jamb, for your Jamb scope scheme of work, you're only required to know the first 20 elements. You're only required to really have information on the first 20 elements. Every good chemistry student should be able to draw a class. There's a periodic table for the first 20 elements, and there's a full periodic table. Class, nobody will ask you to draw the full periodic table. It's impossible. It's unfair. But at least for the first 20 elements, there's a mini periodic table you should be able to draw. For the first 20 elements. We have over 118 elements in chemistry currently. If every day more elements are being discovered. For the first 20 elements, one thing you should first know is that, let me before I even start drawing it. The periodic table is divided into 8 groups for the first 20 elements and 7 periods. Note, the periodic table is divided into 8 groups and 7 periods. The groups are in columns. The periods are the rows. The groups are in columns. The periods are in rows. The groups are in columns, the period are in rows. The groups are in columns, the periods are in rows. We have hydrogen, helium. Hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorinium, sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, argon, potassium, calcium. Class, I've just brought out the first 20 elements periodic table you should know. Class, this is group 1, group 2, group 3, group 4, group 5, group 6, group 7, group 8, or group 0. We call this group 8 or group 0. Class, this is period 1, period 2, period 3, period 4. If we continue to the other elements, you see period 5 like that. But for the first 20 elements is your scope for Jamb. The first 20 elements is your scope for Jamb. So you can see group 1, group 2, group 3, group 4, group 5, group 6, group 7, group 8, or group 0. Period 1, period 2, period 3, period 4. So the full periodic table actually has 8 groups and 7 periods. But for this, we have 8 groups and 4 periods because this is the first 20 element. Class. Groups are also called families. Groups are also called what? Families. Another name for groups in periodic table terms is families. Let me give you small time to write this quickly, to draw the table quickly. Let me give you small time to draw the table. Let me give you small time to draw the table quickly. If you are still with me, say, sir, we are with you. If you are still with me, say, sir, we are with you. If you are still with me, say, sir, we are with you. Someone should give me an update report. Give me an update report so that we can continue. Give me an update report so we can continue. Are you done drawing the periodic table? Okay, thank you. Kelvin says, sir, we are with you. Good. Kelvin says, sir, we are with you. Good. We're almost done. Don't worry, class. So we have groups, are also called families. Class. You can see the elements in group 1. There's something special about elements in each group. I want you to note that elements in the same group have the same atomic number. Elements in the same group have the same atomic number. Elements in the same group have the same atomic number. While elements in the same period have the same number of shells, and I'm going to show you. Elements in the same period have the same number of shells. Elements in the same period have the same number of shells. Elements in the same group have the same atomic number. Sorry, have the same number of valence electrons. Did I say atomic number? Sorry, this is wrong. Have the same number of valence electrons. Have the same number of valence electrons. Elements in the same group have the same number of valence electrons. While elements in the same period have the same number of shells. Elements in the same group have the same number of valence electrons. Elements in the same period have the same number of shells. Let us prove it to you. Look at every element in group 1. Hydrogen is 1, lithium is 3, sodium is 11, potassium is 19. If you check the element table, hydrogen is the first element. When you are listing the first 20 elements, hydrogen is number 1. Helium, lithium, right? Beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, argon, potassium 19, calcium 20. Yes. But let us look at the electronic configuration for each of everybody in this group. Hydrogen is 1, so the configuration is obviously 1. Lithium is 3, which is 2, 1. I hope you all know what's the meaning of valence electron. Valence electron is the electron in the outermost shell of an atom. In case you don't know. Every element has 2 types of electron. Valence electron and inner core electrons. Inner what? Core electrons. Every element has 2 types of electrons. The valence electrons and the inner core electrons. The valence electrons and the inner core electrons. For example, look at someone like sodium 11. What is the electronic configuration of sodium? 2, 8, 1, right? 2 in the K shell, 8 in the L shell, 1 in the M shell, right? Among these 2, 8, 1, these first 2 and 8, 2 plus 8 is 10. They are the inner electrons. This last electron in the last shell, because this is in the K shell, this is the L shell, this is the M shell. This last electron in the last shell is called valence electrons. So sodium has 10 inner core electrons, 10 inner core electrons, and 1 valence electron. So what I'm trying to say is that elements in the same group have the same number of valence electrons. The number of valence electrons for hydrogen is 1. Look at it, 1. Lithium is 3, which is 2, 1. Sodium is 11, 2, 8, 1. Look at 1, 1, 1. Potassium is 19, which is 2, 8, 8, 1. Everybody ends with 1 valence electron. The electron on the last shell of an atom is called the valence electron. The electron on the last shell, the number of electrons on the last shell is the valence electron. Apart from the valence electron, the remaining electrons are called inner core electrons. Inner core electrons. Inner core electrons. So we have valence electrons and we have inner core electrons. But when we notice the elements in the same group have the same number of, you can be asked in the exam. You could be asked in the exam. Elements in the same group have the same number of valence electron. Look at group 2, class. Beryllium is 4, which is 2, 2. Magnesium is 12, 2, 8, 2. Calcium is 20, 2, 8, 8, 2. Everybody has 2 valence electrons. Group 2 means you have 2 valence electrons. Group 3 means everybody in group 3 have 3 valence electrons. Group 4 means everybody in group 4 has 4 valence. Group 5 means everybody in group 5 has 5 valence electrons. Group 6, 6 valence electron. 7, 7 valence electron. 8 or 0, 0 or 8 valence electron. Class. The next thing we need to look at is the other statement we made that every element in the same period have the same number of shells. Class, look at period 1. There are only 2 elements in period 1, hydrogen and helium. That's what they are up. That's why you see that their structure is up. Period 1, they have only 1 shell. Period 1 have 1 shell. If you are in period 1, you have only 1 shell. If you are in period 2, you have 2 shells. Everybody in this period 2, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, have 2 shells. We can prove it. Lithium is 3, which is 2, 1. This is 2, 2, 2, 3, 2, 4, 2, 5, 2, 6, 2, 7, 2, 8. But two shells. Everybody has two shells. Now look at period 3. Everybody in period 3 has 3 shells. 2, 8, 1. 2, 8, 2. 2, 8, 3. 2, 8, 4. 2, 8, 5. 2, 8, 6. 2, 8, 7. 2, 8, 8. 3 shells. Everybody in period 4 has 4 shells. 2, 8, 8, 1. 2, 8, 8, 2. If I continue with scandium 2, 8, 8, 3. Continue with helium 2, 8, 8, 4. Till you get to chromium 2, 8, 8, 5. You keep going till you get to copper. You get to zinc 30. Yes. They all have 4 shells. So elements in the same period have the same number of shells. Please take notes. Now the next thing you need to learn. Every group has a special name. Class, the group 1 elements are called alkali metals. Group 2 elements are called alkali earth metals. Group 3 elements are the boron family. Group 4 elements, carbon family. Group 5 elements, nitrogen family. Group 6 elements, they are called oxygen family or chalcogens. Oxygen or what? Chalcogens. On the body is very important. Chalcogens. Group 6 elements are called oxygen family or chalcogens. Group 7 elements are the halogens. They are the halogens. Why are they called halogens? Because they are salt formers. They are salt formers. Class, group 7 elements are called halogens because they are what? Salt formers. They form salts. Most of your popular salts are from group 7 elements. Most of your popular salts in chemistry, NaCl, this one Cl, they are from what? Group 7. Group 7, group 7, group 7. Salt formers, they are the salt formers. Group 8, obviously, are the noble gases. Everybody in group 8, they are the noble gases, they are the ones that are stable. Noble gas family. Group 8 are the noble gas family. So group 1 elements are the alkaline metals, group 2 elements are the alkaline earth metals, group 3 elements are the boron family, group 4 carbon family, group 5 nitrogen, group 6 oxygen or chalcogens, group 7 halogen salt formers, group 8 noble gas family. Please take note. Class, it's now time to tell you also that the periodic table is divided into 4 blocks as well. The periodic table is divided into 4 blocks. S block, P block, D block, and F block. S block, P block, D block, and F block. Class, I want to give you a simple method to know what block and elements fall under. In the exam, they could ask you to find out what block does sodium fall under in the periodic table. You don't have to start drawing the full periodic table to know that, class. I've already taught you something that can help you to know that. What block does an element fall under? Class, if they ask you to find the block that sodium falls under, I want to give you a simple approach. Just write down the SPDF configuration for sodium. Sodium is 1s2, 2s2, 2p6, right? 3s1. Class, the last block, the last orbital here is the block the element falls under. Sodium is an S block element. Sodium is an S block element. What block does aluminium fall under? Aluminium is number 13. 1s2, 2s2, 2p6, 3s2, 3p1. Class, aluminum is a P block element because the last block is P. A very simple way of knowing, they ask you in Jamb. Are we together? You can do this for any other elements. Just write out the electronic configuration and you can easily know the block that the element falls under. I hope we are still together. 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 Class, there's a particular two special types of elements in the periodic table that are very crucial. You can't talk about periodic table without talking about them. Then you have not taught it well. If you don't mention these two people, you have not taught it well. Please write down the inner transition elements. The inner transition elements. Let us look at the inner transition elements in the periodic table. The inner transition elements. The inner transition elements, class. Class, if you look at any periodic table, you see some separate two rows like this. Those people are called inner transition elements. They are placed, the inner transition elements are placed in two rows at the bottom of the periodic table. The inner transition elements are placed in two rows at the bottom of the periodic table. And they are actually in period 6 and 7. They belong to period 6 and period 7. And the two main groups they are divided into two groups. They are divided into two groups. The inner transition elements are divided into two groups. One is the lanthanides. Two is the actinides. The lanthanides are from element 57 to 71, atomic number of 57 to 71. The actinides are atomic number from 89 to 103. The first member of the lanthanides family is the lanthanum. First member of the actinides family is the actinum. So this guy has atomic number of 57, this guy has atomic number of 89. The first member of the lanthanides and the actinide family. Class, let's look at characteristics of the inner transition element. There are characteristics. They usually ask in the exam, characteristics. This is a popular Jamb question. Characteristics of the inner transition element. They can ask you in the exam. Which of them is not the characteristics of the inner transition? Which of them is not? You must know the one that are first. Class, number one characteristic is that they are all metals. They are all metals. They are all metals. Two is that they exhibit variable oxidation states. They exhibit variable oxidation states. Is this family that you see ion 2 and ion 3? How can it's the same element have two charges, Fe2 and Fe3? Variable oxidation states, they are metals. Many of them are radioactive. Many are radioactive. Many of them are radioactive. 4. They easily form colored compounds. They form what? Colored compounds or colored ions. They form colored compounds. 5. They have similar chemical properties. Please, this is a very serious Jamb point to take note. I won't be stressing it if it's not very serious. I will not be stressing it if it's not very serious. Very, very serious. The last thing before we go for today is the periodicity. I hope we are still there. Good. Someone say we are with you, sir. That's the energy. That's the energy. That's the energy. Let's look at the periodic trends in the periodic table. Periodic trends in the periodic table. Periodic trends. The last thing for today, and we have achieved our target for today. Periodic trends in the periodic table. Periodic trends in the periodic table. Periodic trends in the periodic table. Periodic trends. Periodic trends in the periodic table. The periodic trends are actually patterns in the properties of elements in the periodic table. Patterns. The patterns that we notice across the period and down the group. Remember for secondary school, electronegativity, electropositivity, ionization energy, electron affinity, atomic radius, ionic radius. Those trends we notice in the properties of elements in the periodic table. We call them periodic trends or periodicity. Periodic trends or periodicity of elements in a periodic table. Periodicity. Periodic trends, also known as periodicity. These are patterns in properties. Patterns in properties of elements. Down the group, and across the period. Class, the right term is down the group, across the period. In the periodic table. Patterns and properties of elements down the group and across the period in the periodic table. Let us start with ionization energy. Ionization energy is the energy that is required to remove an electron from an atom. So class, the idea is we define it and then we'll tell you the trend in the periodic table. We define the property and then tell you the trend in the periodic table. Class, ionization energy is the energy that is required to remove an electron from an atom. So when an atom loses an electron, what energy is required for that atom to lose electron? Class, don't forget that when an atom loses electron, what does it become? Positive or negative? It becomes positively charged, right? When an atom loses electron, it becomes positively charged. But the energy required for an atom to lose electron to become positively charged is known as ionization energy. And the trend across the period and down the group. The trend across the period, class, this is very important, you could be asked. And down the group. Across the period, ionization energy increases from left to right. So we're going from left to right, the ionization energy is increasing. But it is reducing down the group, it decreases down the group. Down the group, it decreases. 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 Let's go to the next one, electronegativity. Electronegativity. This is the ability of an atom to attract electrons to itself. Ability of an atom to attract electrons to itself. To become negatively charged. Class, the good thing is that electronegativity also has the same trend as ionization energy. It increases across the period from left to right and decreases down the group. Electronegativity has the same trend as ionization energy. Electronegativity has the same trend as ionization energy. Increases across the period from left to right and decreases down the group. Increases across the period from left to right and decreases down the group. It increases across the period from left to right and decreases down the group. I hope we are still there. I hope we are still there. Someone said, I don't learn more than something today. Oh, that's good. That is good. Someone said, I'm with you back to back. This is the energy. Abigail said, we are with you. Yeah, Desire said, I'm here, sir. That is the energy. Well done, class. Well done, class. I love this. This is 120 minutes of intense chemistry. Of intense chemistry. Of intense chemistry. 120 minutes of intense chemistry. The next one I want to look at is electron affinity. Electron affinity. This is the energy required for an atom to gain electron and become negatively charged. When you gain electron in chemistry, you are negative now, and become negatively charged. Energy for an atom to gain electron. Energy required for an atom. Energy required for an atom to gain electron and become negatively charged. Energy required for an atom, right. Energy required for an atom to gain electron and become negatively charged. Make sure you are writing. Make sure you are writing. Energy required for an atom to gain electron and become negatively charged. Energy required for an atom to gain electron and become negatively charged. Energy required for an atom to gain electron and become negatively charged. Also note that it has the same trend across the period and down the group, the same trend. It increases from left to right across the period and decreases down the group. It increases from left to right across the period and decreases down the group. So far, we have three properties that have the same trend. Who are they? Someone should list them in the comment section. List them in the comment section. There are two properties that have the same trend. What are they? We have what? Electron affinity, ionization energy, and what? Electron affinity, ionization energy, and what? What's the third one? Electronegativity. 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 They all have the same trend in the periodic table. We are almost done. 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 The next one now is electropositivity. 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 Please don't confuse electronegativity with electropositivity. Electropositivity is the tendency of an atom to lose electron and become positively charged. Remember that when you lose electron in chemistry, you are positive. And become positively charged. But the funny thing is that this is the first time the trend changes. When we did the electron affinity, when we did ionization energy, when we did the electronegativity, they have the same trend. But class, electropositivity is where the trend changes. Class, across the period, electropositivity from left to right across the period, it increases. It decreases, or it decreases. But down the group, it increases. Down the group, it increases. Please take note. Down the group, it increases. Across the period from left to right, it decreases, but down the group, it increases. Tendency of an atom to lose electron and become positively charged. Let us go to atomic radius. Class, atomic and ionic radius. Atomic and ionic radius, class, they have the same what? Trend like electropositivity. You could be asked in the exam, which of the following properties have the same trend? So the first three have the same trend: electronegativity, electron affinity, and ionization energy. They have the same trend. Now, electropositivity, atomic radius, and ionic radius have the same trend in the periodic table. That means across the period they decrease, down the group they increase, down the group they increase. Please take note, very, very important. Same thing with a metallic character. Same thing with metallic character. Please add metallic character to this. So metallic character, ionic radius, atomic radius, and electropositivity. All have what? Similar properties. They decrease from left to right across the period and increase down the group. Class, we have come to the end of day 4. Congratulations, we are doing well. Tomorrow is day 5. And before you need like play, we are going to cover the syllabus. You see that we have not missed any day so far. So see you tomorrow. As you can see, for the past 2 days I've been starting earlier than the normal time. Yes, I cannot rest again. Jamb is too close. I cannot, even me, I'm not a student, but I cannot rest. Imagine some students are relaxed. And I don't know buying Jamb for me. I finished school. I cannot rest because I want my students to pass. So I can't even wait for 8 p.m. I started teaching early. I cannot rest. So you too, help yourself. Sit up. Make sure you are reading. Make sure you are doing your past question. Put in more effort. You have to want it so bad. Put in more effort. Be reading like crazy. Read like crazy. Take more questions. Resolve more questions. Set yourself a target of 300. My students don't score less than 300. So I'm also leading by example. So I want you to, so you will not say that you have any excuse to fail. I am leading by example. So I'm taking the first step to show you that I'm serious with you and you must pass your Jamb this year. So tomorrow we can start anytime because Jamb is getting close. Let me tell you something. I told you guys about Jamb camp. My old students, I told you about Jamb camp. We're heading Jamb camp whether I like it or not. So I can wake you up in the minute and start class. Ask my last set. I can wake up in the minute and start teaching. I will just post link. So be alert on that group. I can wake up anytime and teach because a topic can come to my head and I say my student must know this topic. I'll just come up and teach. I'll just post live link. You must pass your Jamb. So we're heading Jamb camp. So drop your TikTok. I can teach anytime. I can teach early in the morning. I can teach anytime. Drop your TikTok, drop your WhatsApp, drop everything and focus on the class. We're in Jamb camp already. We are less than 40 days to Jamb. So there's no time to joke again. See you tomorrow. Anytime I can come up tomorrow and post live link and teach. I'm not joking with anybody here. Are we together? So tomorrow we'll continue. If you stay to the end, congratulations. See you tomorrow with the same energy. Bye. Someone says, sir, today I really understand than other days. That's good. Welcome. That's good. Sir, today I really understand more than other days. Excellent. This is the energy. That's the energy. Good. This is good. This is good. Sir, I really understand more than other days. This is good. That is good. That is good. You're welcome, everybody. Everybody saying thank you. Thank you, too. Thank you for staying. Well done. Follow my instructions. I want you to follow my instructions. Read very well. Read every day. Do your past questions. Put your best effort. I want to see your 300 in Jamb this year. Are we together? I want to see your 300 in Jamb this year. All right. Goodbye, everybody. Good night, everybody. Good night, everybody. See you tomorrow. See you tomorrow. Make sure you go and do your past question. Read. Study. Jack. Put in more effort. Put in more effort. Yes.